I will finish in at most 15 or 20 minutes the proof sketch, the remaining steps of the proof of the quenched central limit theorem, of the quenched central limit theorem for random walking, in this type of random environment under this h-1 condition. And when I'm done with that, I will be looking at the cases when you don't have h-1, when you don't have an upper bound, this type of upper bound on the variance, what happens there? And we will see interesting things there, namely super diffusivity. Namely that the diffusion is faster than normal. So let me prove the quenched. So what I'm going to prove is this theorem, the quenched central limit theorem for random walk in doubly stochastic or in doubly stochastic random environment under h-1. I don't state again all the conditions. You know what it is about. I have a stationary field of jump probabilities on the lattice ZD, stationary and ergodic, and there is this double stochasticity condition, and there is the h-1 condition, which means that the flux, how do you call it, the local drift function is in the domain of Laplacian to the -1, right? Which a priori gives an upper bound on the second moment, on the variance of the annealed variance of the displacement. And what I'm proving is a quenched central limit theorem. So namely what I'm proving is that under the conditions stated, which I don't repeat, under the conditions, remember what the conditions were. So that's double stochasticity, ellipticity, and what I call L. Okay, so I called it h-1. I add here an epsilon, which is sort of a strange way of denoting. So I have the h-1 condition on the anti-symmetric part of the jump rates, but as you remember that meant an L2 square integrability condition on the stream tensor, but I assume a bit more. I assume L2 plus epsilon integrability on the stream tensor. So let me say this means that S sub k integral on omega S sub k on the 2 plus epsilon d pi is finite. Okay, call it the maximum over k in E. This call it S upper star, and a similar thing we do maximum k and L integral on omega hkl d pi, call it h upper star, and these are finite, so 2 plus epsilon. So these are the conditions imposed, and under these conditions what I claim is the following, that for almost all, so the theorem is the following, under these conditions, for almost all omega, the central limit theorem holds for the displacement. And I'm not doing more formal things now. And I sketch the proof, the 4 steps of the proof. The first step is the following, so sketch of proof. Mind that we have proved already the annealed version of this theorem. The first step is quenched tightness. Quenched tightness, and this is exactly what I proved yesterday. Yesterday I proved that there exists a constant which is finite, which depends only on these guys, S lower bar, I have a S lower star, S upper star, H upper star, and dimension, depends on these guys, such that for pi almost all omega, and there exists a T starred of omega which is finite, such that for T larger than T starred omega, E omega of absolute value of xt, let me divide it by square root of t, is bounded above. So this means it's more than just tightness. It means that for the first moment of the properly scaled, and this is what I proved yesterday. Now let me emphasize something. A weaker statement we have from something much less. I wasted, between quotes, one full lecture with this Nash story, and I wasted this lecture with at least the second half with a Nash story, because here I need a quenched, almost sure tightness. I do have the annealed tightness actually from the h-1 condition directly. So if I integrate out over omega, I have a similar thing for the second moment, an upper bound for the second moment. But that's not enough. So this is, if you wish, abstract homework for you, that from annealed tightness, quenched tightness doesn't follow. Right? And this is what I need. So this at least tells me that in a quenched way, almost surely for almost all environments, the properly scaled random walk at least doesn't flow away. Right? Done. This is done yesterday. Second step, and this is an idea which I want to convey, and it goes back to Sergei Kozlov back in the 80s, or Varadan, Kozlov. There were a number of people who worked on this type of problems, but let me call it idea of Kozlov, is construct so-called harmonic coordinates. So harmonic coordinates is the catchword. And let me tell you in plain words what that means. I am trying to find, this means the following, find a field, let me call it psi, and let me write x omega. So from x to x, so it's a random field on the lattice. This is on the lattice. And this will be RD valued. An RD valued random field on the lattice defined on the probability space omega on which my so this depends on the environment. It's a functional of the environment, which has some properties. The first property would be that it is a field of stationary increments, That means its gradient is a translation invariant object. So that means the following, that let's say call, this is psi, let me call u. I think I didn't use u so far. Maybe I look at my notes not to make too many notations. No, I denoted this one in my paper, not phi, but capital theta. This is a capital theta, and its gradient will be called the lowercase theta, so call such that capital theta of x plus k omega minus capital theta of x omega be a lowercase theta of tau x k of tau x omega. What do I mean by this? There is a stationary field of gradients, which is the gradient of this field. This field may be only, this shows you that this is of stationary increments. It may not be stationary itself. Clear? But due to the fact that this is a gradient, this has this gradient condition, this field. So if you sum, this is a gradient. So if you sum that increment plus that increment is the same as summing that increment plus that increment. Overall, the circle sums of this guy, that's what we call a co-cycle. But it's a vector valued, mind, it's a vector valued co-cycle. Right? So I want to find something like this, such that for all omega, for omega fixed, xt, let me do it this way, and this is zero mean, of course, zero mean. So let me say this way, xt, I may put here an omega, but I don't put, because it depends also on the environment, right? Minus, or plus doesn't matter, minus theta at xt, so this process, be a martingale. Be a martingale. Is it clear what I mean? So I correct, this is not a martingale. For ordinary random walk, this is a martingale. Right? But for the random walk in random environment, it's not a martingale. The local expectation of the next step is not zero. But maybe you can correct it. Maybe you can find a field like that. This is an ingenious idea, actually. This is S.M. Kozlov 85 or something like that, maybe before 85. And I don't claim that he formulated exactly in these terms. This is a streamlined presentation of Kozlov's idea. So try to find a field which is of stationary increment defined on the same probability space, such that this object is a martingale almost surely, for almost all environments. Right? If you write down the martingale condition, this will lead to an equation for this guy. You have to write down the expectation of the increment of this guy, infinitesimal expectation, infinitesimal time of the increment of this guy is zero. I write down the equation. This is an equation which I write down now. The equation will mean the following: sum over k in nearest neighbors, so k nearest neighbors. If I am at site x, then I jump along the edge k with rate p sub k omega. That's the rate of jump, right? And I have an increment like this, and an increment coming from here. Let me revert them. So I have theta of tau x omega, tau x omega, theta, small theta k of tau x omega be equal to sum over k in E, p sub k tau x omega times k. I just put one on one side, one on the other side. So this is the expectation of your next step. And this is the expectation of the change of this random variable, because you jump along that, put in the increment of that field. And it's true for any, that's why I wanted this to be of stationary increment, to erase here tau x. This is true for all tau x. That's the same writing it for omega. So this is the equation I have to solve. It looks a tame equation, but it's a very difficult one. And mind that it's a vector, well, these are actually D equations. These are D equations because this is a, because these are, K is a vector, K is a vector in Rd, and theta sub K is also a vector in Rd. So you have to solve it for all component-wise. Now this is a difficult equation, and you want to solve this equation let me give it a star. Solve star for theta k omega being a gradient. So with the condition, with the additional condition that theta is a gradient, that means theta k omega plus theta L tau k omega equals theta L omega plus theta k tau L omega for all k and L on any placket. So this is the additional condition and expectation of theta 0. Because you always have some trivial solutions. I'm not sure, but you may have trivial solutions which I don't want to go for. I mean, integral with respect to pi. Zero mean. Right? These are additional conditions. Solve that equation. Now, I will not go to show you, because it's again a lot of transformations and so on. Write it down. This is an equation in Hilbert space. I mean, not 1D equations. These are equations in my Hilbert space. And after some massaging, which you can find in the paper, and I'm not going to repeat because it's similar type of things which I've done already. Write down the operators which appear here. Of course, you will have the operators, the shift operators. No, the shift doesn't appear, but the shift appears in the condition for theta. So put together the things, and then the shift operators appear. All operators I have written so far on the blackboard appear. And after some massaging, you will arrive to a problem we have solved. So this reduces, which I'm not going to show you, but you look at the paper and it's indeed natural things what are done there, reduces to solving I will make one more comment. Before I finish this sentence, I make a comment. Note that what you have on this side, is exactly the local drift of your random walking random environment, and our assumption, h-1 assumption, is that this object as function of omega, this element of the Hilbert space, is in the h-1 subspace. Right? So this is in the h-1 subspace. This is very important because otherwise we couldn't solve the equation. But it's not enough. Reduces, so using that and using all what we have done so far, it reduces after some reductions to an equation like, just trust me, to solve identity plus b of f equals g. There are some transformations. This g comes from Laplacian to the -1/2 applied to this guy, and there are some transformations in the story. With g given. And b is my old friend, which is s to the -1/2 a s to the -1/2. Between quotes, but for which I already can take away the quotes because I proved that this operator exists as a skew self-adjoint. This is an unbounded skew self-adjoint operator. This was my technically main part in 2 lectures ago. Right? So this is proved to be, B is proved to be a skew self-adjoint unbounded operator. Unbounded, closed skews, truly. So its spectrum is on the imaginary axis. So this is invertible, so it's trivial now, isn't it? Formally trivial, but what we have done so far is not trivial. Formally trivial, this is invertible because I have identity plus an unbounded but skew self-adjoint operator which has its spectrum on the imaginary axis. So the inverse, this is an invertible operator with its inverse having norm 1, or at most 1. And invert it and you solved it, you find an f, which is a solution, do backwards all the transformations, you have done just the massaging backwards, and you have done, you are solved. It's not the case that I have a formula. It's not the case that I have an explicit formula for this guy, but I prove its existence, and actually also its uniqueness, due to the same thing. Just in parentheses for those of you who know this type of, so it's a sort of Fredholm alternative I'm doing here, because first I proved there is at least one person who smiled, so he understands what I'm saying. First I proved skew self-adjointness of this guy by proving that there is no eigenfunction belonging to a particular eigenvalue. So, and that's uniqueness. And from uniqueness follows existence. So this is what we call Fredholm alternative, but that's just a comment, right? So indeed, this looks now very simple what's on the blackboard, but mind that deprecation is by no means simple, and the previous ways of solving it are very, very cumbersome and complicated. This is also complicated, but it's a clean picture. So what is the functional analytic background? You can solve it because in the background there is an equation like that with a skew self-adjoint object here. Done. I'm not giving details here because it's just repeating. It's funny, I enjoy it, and it's enjoyable for those who like this type of thing, but probably you learn more from it if you look at the paper and. Third step. Third step is trivial. Third step is trivial because once I showed it, take this process, call it some name, say y of t. This is a martingale. I proved that there exists the harmonic coordinates. The harmonic coordinates are unique. I defined this object, which I call yt, this process, which I call yt, which is a martingale, it's a quenched martingale with a fixed omega, but in the annealed setting. So if I take also probability with respect to the bigger probability space, in the annealed setting, it's a martingale with stationary and ergodic increments. Not in the quenched, in the annealed setting. So for this martingale, the martingale central limit theorem applies. For this martingale, the martingale central limit theorem applies. So the third step is apply martingale central limit theorem to the yt, which is just a standard thing to do. So at the moment I have the martingale central, actually I not only central limit theorem, invariance principle for y. And what's left is to prove that the difference of y and x is not big. It's smaller order than, and the same philosophy comes in. This is a co-cycle, a field of stationary increments with zero mean, which is in principle sublinear, but you have to be very careful here. Now, if this is sublinear in space, and I have the square root upper bound, I have the tight bound on xt, then this is smaller order than square root of t. Now, you have to make this rigorous. This is a non-rigorous argument, but it tells you what happens. Let me repeat. A field of stationary increments on ZD, in some weak sense, is sublinearly increasing. Zero mean. I always mean zero mean. But weak sense, take weak sense. It's easy. This is a subtle thing. I'm not going into details. it's a subtle thing. In one dimension, it's just ergodic theorem, what I refer to. In two and more dimensions, you have to refer to, I tell you, a catchword, and if you open one of your favorite books of ergodic theory, for example, Krengel's, some more modern book on ergodic theory, you find something which is called the, oh my gosh, how is it called? Unconditional, in the multidimensional setting, the unrestricted ergodic theorem. Look at, this is a catchword, unrestricted ergodic theorem in 2 and more, on ZD, which is a very subtle thing. You don't have that strong results as almost sure convergence. You have some logarithmic problems. But look at it. But anyway, the last step, step 4, let me erase this. Step 4, prove that for almost all, for pi almost all omega, the quenched way, probability that theta 1 over square root of t, theta x t, okay, larger than delta converges to 0. As t goes to infinity. So that means that theta xt divided by square root of t converges in probability to 0. I have done something similar already once, but not in the quenched, in the annealed setting. Remember, I've done something similar, but in the annealed setting, and all what I've done in the annealed setting has to be done in the quenched setting, and that's much more demanding. And this is the point where I use the tightness from the first step. Here is the tightness used from the first step. Put together all these things, I think the idea is clear. I think I've given you sufficient input on what kind of techniques are used. So I consider this theorem proved now. Any question related to the central limit theorem problem done so far, because I will jump now to the complementary problems, namely super diffusivity, when h-1 doesn't hold. So please ask your question, or of course you can ask your questions till Friday noon at any time. But if you have anything unclear you want to ask now or comment on now, let me hear. Yeah?
So if theta, because theta is it a first order fraction?
Is it? Yes, that's what in the PD community or the homogenization community, you come from homogenization background, right? They call it corrector, right? They call it corrector. Yeah. Harmonic coordinate, I call it, okay, Kozlov called it harmonic coordinates. I think in this context, harmonic coordinates is a very, very good name. Actually, this is the harmonic coordinate, okay, just for so the theta is the corrector, and this function, which maps x to x minus theta x, this is what I would call harmonic coordinate. So change the coordinates. It's like distorting your space a little in such a way that your walk is on the distorted coordinates, your walk is harmonic. Your walk is a martingale. Yeah, that's correct. You're right. Coordinate minus corrector equals harmonic coordinate. More comments or remarks or whatever? No. So let's go now and ask the complementary question. Mind that all what I've done was done under condition of h-1. And let me repeat what h-1 was. h-1 was the following. Take the symmetric part of your random walk. In these cases, the symmetric part in my previous case was always a simple symmetric random walk on ZD, and integrate the drift field along the trajectory of an independent symmetric random walk, simple symmetric random walk, divide by square root of t, and prove diffusive upper bound for that. If that is finite, if the variance of this object is finite, the asymptotic variance is finite, that gives a very efficient upper bound on the variance of my original question, and that's a sufficient condition. And we don't know a better, closer to necessary sufficient condition at the moment. Now, when H minus 1 doesn't hold, and let me give you examples again. In the first lecture I gave, but I want to repeat some of the examples. So what happens when H minus 1 fails? So what if H minus 1 fails? Right? And let me go back to the examples. I gave some examples, now I repeat only those ones where we do not have H minus 1. One of the examples was the Manhattan. I draw two-dimensional examples because the blackboard is two-dimensional, but yeah. So this is the Manhattan. So remember, I oriented the avenues randomly. These are randomly oriented avenues and randomly oriented streets. At each single street, at each single avenue, you toss a coin and orient them one way. And as a driver, you drive here, and whenever you arrive at a corner, you choose with a coin toss between the two allowed directions. Right? Clearly, it's doubly stochastic. That means that the drift, the local drift, is divergence free. You have that many in point. At each side, you have 2 in, 2 out. Clearly, it's zero mean, so you don't have an overall drift which takes you away because orientations to the east and to the west, at one hand, to the north and to the south are equally likely. What does it happen? And of course, you could imagine it same on ZD. This is on Z2, same on Z3, Z4, and so on. Now, it's the symmetric part of the walk exercise for you. If you write down the symmetrized, it's just ordinary random walk. The symmetric part is ordinary random walk. So if you add the rates in oppositely oriented edges and you put those conductances, that's just ordinary symmetric random walk, right? Homework for you, that H minus 1 fails in dimensions 2 and 3 and holds in dimensions greater than or equal to 4. So you just have, what you have to do is, you have this field, you take an independent ordinary simple random walk and integrate the field, I mean the expected, the drift, along your ordinary random walk, take the variance, divide by t, variance over walk and randomness of the environment. It's an elementary computation. It's a very fun computation. It's a nice computation. Do it, and this is what you will feel. See that it fails badly in 2 dimensions. When I say badly, it fails by a power law of time. It fails marginally in 3 dimensions by a logarithm, power of logarithm, and it holds in 4 and more dimensions. Is it the case that the walk itself, this thus tells me that the diffusive upper bound doesn't hold. I don't have that simple diffusive upper bound which comes from H minus 1, that who knows what happens, right? This is one of my examples. Actually, I know what happens in 4 and more dimensions because my theorem holds in 4 and when H minus 1 holds, my theorem holds. So in 4 and more dimensions, I do have central limit theorem, but I don't know at the moment what. I tell you from start that it will be super diffusive. Another example will be continuous, will be diffusion. And this will be the example I will analyze to the end because notation is simplest. And not only because notation, because this is done well. This is fully done. Take in R2, let, I don't give a name to it, but let GFF be the Gaussian free field pinned down at 0. Now, those of you who don't know, who know, hands up, who are familiar with Gaussian free field. Actually, in the continuum, it's a tricky thing because it's not a field, it's not a function, it's a distribution, it's a random distribution. And when I say pinned down to 0, I mean, on the lattice, you easily can imagine. There were so much words about Gaussian free field so far. But it does exist as the pinned down version, it does exist on the continuum. I will tell you it's a Gaussian field. But anyway, I will convolve it with a smooth function locally to make it truly a field. So convolve it with something I just call u, where u of x, where u is something like this, whatever you love, an approximate identity, an approximate delta. If you love, it could be e to the minus x squared with some constant there, but it could be something else. Doesn't matter much. What matters is that it's smooth, infinitely smooth, decays sufficiently fast, say exponentially fast, and say rotationally symmetric, just to not destroy the rotation. What I mean that the Gaussian free field is convolved with this u, right? So this will create a field, a true random field over R2, which has stationary increments, and the Gaussian I could write down its covariances, but I will not, because what I need is not this guy, but I need the two-dimensional rotation or curl of this guy. So take the curl of this, and call it f. And call it f. So f is a vector, is a random Gaussian vector field, which is stationary and ergodic, and I will write down its covariances and all that, and that defines it perfectly well, right? So f is a Gaussian, f is smooth, ergodic with respect to space translations, Gaussian vector field. So this is a vector field. It's a, by the way, what is curl? What is the curl in 2 dimensions? The curl of a scalar field, of a height function. X component is d by dy, y component is -1 times d by dx. Right? I write down the covariances, yes? The covariance will be so x fx, x maps to fx, which is actually random. It's the last time I wrote this up. No, it's not the last time, but I write omega there. Good. So this is a Gaussian vector field. I write down its covariances. Fix, fjy. Let me write this way expectation of the field. By the way, zero mean. Zero mean. I don't add constants because that's always just a nuisance, right? And the covariance, I call the covariance k sub ij y minus x, which I could write down. It's related to the, it's actually, okay. I write down the Fourier transform of this guy because that's the easiest. With k hat ij p, this is the Fourier transform. Now it's continuous Fourier transform. It's integral, right? Will be still pi tilde pj tilde by p norm squared times this squared. So let me call it v hat p. I tell you in a moment what is what. Where p hat tilde is, let me use the notation of Asaf from last days, is TP is rotation by 90 degrees, say in anti-clockwise direction. So this is P1 tilde is P2, P2 tilde is minus P1. This comes from the curl, right? This 1 over P squared, so this comes from the curl. 1 over P squared comes from the Green function, from the covariance of the Gaussian free field, right? And V hat P is just the square of U hat P. is just the square of u hat p. So take a function v, which is a convolution square of u, and it's the Fourier transform of that guy. Right? Anybody has some problems yet? So I defined, this is a perfectly well-defined Gaussian random vector field, divergence-free, easy to see because it rises like a curl. If it's a curl of a height function, it's divergence-free. So the divergence of f is identically 0, almost surely. Right? And now I define, so essentially what I have to put in here this smoothing guy, because otherwise things don't make sense. But what I speak about is the rotation of the Gaussian free field. Just I have to smooth it out because otherwise it doesn't make sense. Right? And now I define a diffusion, dxt, be dbt plus f of xt dt. So the diffusion is like that. The drift part comes from this vector field and add noise, add Brownian noise. This is the diffusion I'm looking at. Right? Since this is a divergence-free vector field, all my philosophy so far is valid. I did it on the lattice, but it's valid in continuum. So the environment as seen, if I travel with the diffusive particle and I note this field, I make a film of this field but seen from the random environment, I will write down from the random Walker, that will be a stationary Markov process. Right? I will make it clear in a moment. But mind, if f was if I wouldn't add the noise here, if I took just this deterministic object, then this dxt would just follow the level lines of the Gaussian free field. So we'll go around deterministically on the level line with some varying speed, but we'll stay on the level lines. Now the noise pushes it away. The noise makes it choose random level lines. So like from time to time, jump from a level line to another one. Of course, it's not from time to time because it's a continuous change, right? And now let me denote eta t be f of xt plus x. This is exactly, eta t of x. And I think about this guy as eta t about the field. So this is the environment as seen by the random Walker, right? This is in a function space. My omega is what? My omega is omega is C infinity, infinitely differentiable from R2 to R2, which are curls. If they are curls, that means that divergence of omega is identically 0. And I also impose some increased condition just to make it a metric space, this function space. Slow increase of all partial differential. Let me not write down, there are some semi-norms, but this is just a nuisance. It's just omega. Let me just be pretentious, and I write here L, M, R, finite. L is 1 and 2. That means omega has two components because it's a two-dimensional vector field. M denotes any kind of partial derivative. And R denotes somehow control of increase at infinity. I don't spell it out, just I tell you this means that I look at this space which is infinitely differentiable functions which are divergence free and which increase slower than any power of x, which increase together with their whose all partial derivatives increase slower than any power as you go away to infinity. This is a nice, it's an infinite dimension, it's a function space, but it can be metrized. So the topology defined by this semi-norm is a metrizable topology, so this is a decent function space, right? On this decent function space, I define a probability measure, which is the Gaussian measure I told you. A probability measure which is on omega, which is Gaussian. So that means under which any finite omegas are jointly Gaussian, right? And their covariances are like here. So integral of omega d pi is 0, and integral of omega I x omega j y d pi equals this k I j y minus x. This is a Gaussian measure concentrated on this infinite dimensional space. It makes sense to define a Gaussian probability measure on the function space, right? And what I claim that this Markov process, that this process will be a stationary and ergodic. This will be stationary ergodic on omega with this pi. These are facts which can be checked. Stationarity follows from the fact that it's divergence free, and ergodicity from some abstract arguments. So eta t is ergodic on omega pi. But mind that this is a very concrete space. Now this is a very concrete function space with a Gaussian measure on it, right? And my Hilbert space will be, okay, let me say L2 of omega pi is my Hilbert space. But mind that this omega pi is spanned by Gaussian random variables. So this is what it has more structure than just a Hilbert space. This is not just an L2 space. It's an L2 space over a Gaussian measure. I have Hermite polynomials. I have Fock. This is a Fock space for those of you who know Fock space. Or for those who like the same thing, name Wiener chaos, call it Wiener chaos, right? So this is H, but H is sum n from 0 to infinity of H sub n closed, where H sub n is the space spanned by all possible n-order Hermite polynomials of these Gaussians, right? Take whatever omega, so Hn is the span of let me just say erm n, that means all multinomial Hermite polynomials. I don't write down formulas. These are polynomials. You know how to write down the formulas for them. Of omega, say I1 x1 to omega in xn. So take all possible n tuples of the omegas, which are Gaussian random variables, form the Hermite polynomials, which are explicit formulas, and the subspace spanned by those will form my H sub n. And by Gram-Schmidt orthogonalization, you see that these H sub n's are orthogonal to each other. That's why Hermite polynomials are what they are interesting, right? So this is an orthogonal decomposition. All these spaces are infinite dimensional, except H0. H0 is just the constant functions. The rest are infinite dimensional. H1 contains all linear. In H1, only Gaussians appear, all possible linear combinations of these omegas with closure. In H2, all possible quadratic expressions, combinations of quadratic expressions of the omegas, but orthogonalize to the linear expressions. And go on like that. So Gram-Schmidt with Gaussianness is what you see there. And this is what they call Fock space in physics, right? And now let me tell you what we do. By the way, this what I'm speaking about is from a paper I've done with my ex-PhD student and colleague, Benedek-Valco, so is published in and you find it towards the end of the lecture notes. Not the last one, but the one but last one, I think. Denote just E T, which is just B, the expectation of xt squared. By this I mean the annealed expectation. Annealed expectation, this means integral on omega E omega xt squared d pi omega. So you take with fixed omega, you have the process defined with fixed omega, which is somewhere there. With fixed omega, which gives the coefficients, take the second moment, take the variance, or no, this is not the variance, conditionally this is just second moment, and integrate out with respect to the field, randomness of the field, you get the annealed. It's easy to see that the annealed expectation of x is 0. So this is the annealed variance of the displacement. And denote by E hat lambda the Laplace transform of this guy. So this be integral from 0 to infinity e to the minus lambda t, et dt. Right? Now, if this was diffusive, this process were diffusive, h minus 1, no, sorry, this is more than h minus. If this process were diffusive, then this E sub t would behave linearly as for large t. Right? If it was diffusive, then this divided by square root of t, and squared would be tight, you would get something like constant. This would be linear in t, right? Take the Laplace transform, it would behave like 1 over lambda squared at lambda equals 0. Right? Theorem, or no, first conjecture and then theorem. I formulate the conjecture in vague terms because anyway it's a conjecture. Conjecture Et is of the order t times some log t power. With yes, so let me say it square root of t times this squared. So t times log t to the 2 gamma. Right? T times log t to the 2 gamma with gamma equal 1/4 for some reason, but let me put a question mark there. Anyway, it's a conjecture. The conjecture is that this is marginally super diffusive. Marginally, that means that you have a logarithmic correction in the problem, and actually I also have a guess for the logarithmic correction. But anyway, this is a conjecture, which means that E lambda would be when lambda goes to 0. So this is interesting when lambda goes to 0. This is interesting when here t is large and here lambda is small. Right? Which means that E lambda should be something like lambda squared, lambda to the minus 2, times log lambda to the 2 gamma. That would be the order. We are far from there. What we prove is, and I will sketch this proof because it's very, very instructive in my opinion. It tells you physics. It tells you what happens. Theorem. And this is one of the main results you find in that paper, which is the last but one in this green booklet. So this is myself and Valco. 2012 published, and it's the following. E hat lambda is less than a constant times lambda to the minus 2 log lambda, and greater than another constant, call it small c, lambda to the minus 2 log lambda. So mind that the two don't match, and neither one matches with this one, because my guess is that gamma is not 1/2, but 1/4. Right? This is a bit short. So how should I put it? Morally, this means that E hat ET is less than constant t times log t and greater than constant t times log t, rather than what you see there, but only morally, because you need some Tauberian inversion to get from the Laplace transforms, and we don't have the Tauberian inversion. Actually, what don't have time to, it means for the ET that in some averaged sense, ET is between those two. So what I want to emphasize that, and what's important here, not the upper bound drops out from the h-1 estimates, which are those type of estimates, which is not very surprising. The lower bound is the interesting, which indeed proves super diffusivity. Not quite what we want, but at least super diffusivity is established. Right? And this is what I'm going to tell you in a moment. So this is what I will concentrate on from now on. But before I do that, let me see, how do I stand with time? For those of you who love lattice rather than continuum, better not. No, I don't waste time with the lattice model. The corresponding lattice model, I speak to those very few in the audience who know these things. I gave an example. Take the 6-vertex model on Z2, define that vector field in terms of the 6-vertex model, take a random walk on that 6-vertex model, and try to prove this for the same. We can't do that because we are very far from that, because for a reason I will tell you later. We are close to another result with the same Benedek-Walko, not quite done yet. Namely, take the 2-dimensional lattice, take the Castellani's Dimer model. I speak to very few now. I'm sorry, I don't want to waste time to defining new things. Take the Dimer model on Z2 and orient those edges where you do have a dimer, say from black to white, with a power, say, of 3, and those where you don't have dimers from white to black with a weight of 1. So at each black vertex, you will have 3 edges of weight 1 coming in and 1 edge of weight 3 going out. And at each white sublattice, you have the opposite. So it's divergence free. Take a random walk on this random lattice, and the same theorem should hold. But there is a difficulty we are struggling with, so we are not yet through. It's very much the fact that these are Gaussian stuff which we deal with here helps a lot, as you will see. Good. So let me go into the ideas of proof of this type of theorem. And before I erase, let me just tell you again that the point is the following. If you don't, whatever small randomness you could put here, and it's true, just that epsilon will enter in as a constant. That's a very strange thing. If you don't have any randomness, then the motion is confined on compact, on level lines. And the level lines are compact, that's an easy thing to see. If you add the minimal noise, whatever small noise, it becomes super diffusive. There is nothing in between. Right? There is no diffusivity in between. No matter how small epsilon noise you add, this pushes randomly between the level lines of the Gaussian free field and makes it super diffusive. So combination of these two make it super diffusive. It's fun. Which shows that you can't expect, in a simple way, continuity of the limiting variance in the parameters of the problem. Because here is a very simple example. You have one very simple parameter of the problem, the epsilon, and you have a total discontinuity when epsilon goes to 0. Jumping from confined to super diffusive. Okay, now let's go into details. I told you what my Hilbert space is. I told you what the Hilbert space is. It's not there anymore, but you remember. And now I have to define some operators. So from now on, unfortunately for those who don't like this type of thing, I will need operators on these Hilbert spaces, and I will have sort of Laplacians, sort of gradients, and creation and annihilation operators. I'm sorry for those of you who don't like this type of thing. And I will have Wick polynomials. Hands up who know what Wick polynomials are? Few, but I will sort of explain what the Wick polynomial is. And actually, we don't need many of them, just for the definitions. So a Wick polynomial, I will denote it like this, in this particular case, I1 x1 omega I n xn dot is denoted like that, and a very fast definition is the following. These are Gaussian, these are random, these are my Gaussians, right? These are functions in my Hilbert space are Gaussian random variables. Take the product and so, okay, do it. It's just the same as Hermite polynomial. So take the product and orthogonalize it. So take the orthogonal complement to all the previous subspaces. So I can define them only sequentially, going from n to n plus 1. So as you define the Hn, the space Hn, you can go to Hn plus 1, take an expression of power n plus 1, and take Gram-Schmidt orthogonalization to all the previous ones, and that's the Wick polynomial, right? And this will be actually a polynomial sort of expression on this guy and subsets of these guys. So it's indeed a polynomial on the omegas of power n, right? And I1 to In is 1 to 2 because these have two components. I1 In is always I1 IR is either 1 or 2 depending on which component of omega, and XR is in R2. Okay? So Wick polynomials are not magic objects, are just polynomial expressions of my basic Gaussian random variables in such a way that anywhere when you see these two double columns, it means that it's orthogonal to any expression of lower order of all Gaussians in the problem, right? I define gradient type of operators, nabla L acting on a Wick polynomial, acting on omega I1 x1 omega I n xn will be, and these two double columns indeed make life unpleasant because I like to put at the definition a double column, but I shouldn't now because that makes indeed awful thing. Sum over R goes from 1 to n. Let me just put the dot. You have the r's here, I sub r, x sub r, but take its derivative. Take its L derivative, dl, that means d by dxl, right? And the rest unchanged. And it makes sense because my fields, if I give you the Gaussian measure, it's an exercise, not a totally trivial exercise, to prove that almost surely, since that function v was infinitely differentiable, almost surely all the omegas are infinitely differentiable. These are Gaussian fields which are almost surely infinitely differentiable. In particular, these derivatives do make sense. And this is also Gaussian. It's a linear expression in the previous ones. Right? I define a Laplacian in my Hilbert space. The Laplacian in my Hilbert space will be, let me just define it, sum over L goes from 1 to 2, nabla L, nabla L. This is a practical definition. You could define it coordinate free, give easily a coordinate free definition, and also for the gradient, but this is the cheapest thing I can do. And just write down the expression and you will see what happens. And you easily check that these operators map H sub n to H sub n. So act diagonally in the grading of the Hilbert space. Of course, you could see the expression, they act diagonally, because if you had an n-order expression, you differentiate, as you learned it in high school, how to differentiate the product, and you have an n-order expression. No question, right? So act diagonally on the Hilbert space. Good. Mind, as we are not on the lattice, these are not anymore bounded operators, but they are well understood operators. Shifts. I mean, defined in terms of shifts. No problem with their definition. But I also define now some creation operator, A star of L and A of L, which act on my Hilbert space, and namely this will raise H sub n to H sub n plus 1, and this will map H sub n to H sub n minus 1, respectively H sub 0 to the 0 element. Right? Which I'm going to define now. These things are really not difficult and standard. Some people know them under the name, if you have some physics background, then you speak about Fock space and creation and annihilation operators. If you come from probability, you speak about decomposition according to Wiener chaos, and I don't know how you call these operators in probability. How do you call them? I don't know, but you have them. Or Maria-Wien calculus have their jargon on that these are all the same things. Right? I define A star of L. A star L acting on a weak polynomial, on a weak monomial, I1 x1 omega I n xn will be weak polynomial of one higher order, omega L at 0, omega I, and the rest. I1 x1 omega I n xn. By the way, here, when I write down these things, order doesn't matter, of course. Right? So I take the weak polynomial. What do? I take this polynomial expression, I multiply it with this Gaussian, I orthogonalize to the subspaces up to Hn, and I get the polynomial expression of these n plus 1s, and that's it. Right? That's Gram-Schmidt, nothing more. And let me not define the adjoint of this guy. It's homework for you to, of course, you find it in the notes, to find the definition of the formula for AL. I don't write it down. By the way, I only define my operators as they act on weak monomials, but by linear extension, you have it on the whole subspace. So this is full definition, actually. And we are done with the definition of our basic operators needed in the sequel. What I'm going to do now is to speak about the infinitesimal generator. So I have the process eta t, which eta sub t, which is the environment as seen by the random walker, right? Define the semigroup BTF of omega be E omega f eta t. What does this mean? Start your process from the environment omega. Let the process run, let the diffusion run till time t. Shift yourself to the position of the random. Look around. That's your actual environment now. Take conditional expectation, right? This is a semigroup. This is semigroup acting, PT acts on H. It's a contraction semigroup. It has an infinitesimal generator. PT is e to the TL as usual. And now I will write down the infinitesimal generator. That's the point. What is the because that contains all information. Now, it's a very beautiful object. The infinitesimal generator in this case, this is an operator, a linear, in this particular unbounded linear operator, acting on the space H. And it will have the form 1/2 Laplacian, mind Laplacian as defined there, plus sum over L goes from 1 to 2 because we have two components. I have something like nabla L A starred L plus A sub L. Do I do it well? The other way around. Nabla L. Which looks like an abstract object. It's absolutely concrete. I gave you all operators here. And what's fun about it, it has the form somehow like a quantum field Hamiltonian. It's simpler, but it's like, so you get the Laplacians, you get, if you open a book on quantum theory, on quantum field theory, you will find operators of this form acting on Fock space, or of similar, not exactly this one. So it's a very funny thing that these similar objects appear. Now, these are very concrete objects. This will be the symmetric part, and this will be the anti-symmetric part. Easy to check. And let me call this guy A plus, and this guy A minus, because this raises from Hn to Hn plus 1. This lowers from Hn to Hn minus 1, right? I don't write it down. So this is my operator, which is absolutely concrete. And now I do what I have to do. I don't derive this because that's longish, but it relies on concrete computations and the concrete expressions of the operators. And what goes on is analysis, or if you wish, spectral analysis of this operator on that Gaussian Hilbert space. Now, I write xt, that's the displacement of my diffusion, is xt minus integral from 0 to t, our old friend, of phi eta s ds plus integral from 0 to t of phi eta s ds. That's the Martingale decomposition, well known, where I have to choose this phi is a function, phi is an element of my Hilbert space, so is a function over the omegas, in such a way that if I subtract it, I make this a Martingale. Anybody wants to help me how to find this phi is a simple object. How should I remember what the stochastic differential equation was? The stochastic differential equation was dxt equals dbt plus fxt dt. So the infinitesimal drift is this guy, right? But this is exactly, this should be phi of eta t. So a function of omega, and this is the environment seen by the random walker at this moment. But what is phi? I tell you what is phi. Phi of omega is mind, omega is a field, omega is a divergence-free vector field. Phi of omega is omega at 0. This is omega at the position where I am. Mind, eta t was defined as, so this is exactly the field at the position where I'm. Anybody hands up who understand what I'm saying? So here is the problem. This is a martingale, don't care about this. I have to prove super diffusive lower bound for this. I have the operators, I have the function, I have everything. Right? Recall the variational formula. Recall the variational formula, which was done in the first day. First of all, let's see that h minus 1 fails. First of all, let's see that h minus 1 fails. First of all, let's see that h minus 1 fails. How should I do that? To convince you. Okay, I just write on the, so the h minus 1 formula is the following, that the integral over p, so this is rd because now we are not on the lattice. This will be an integral over Fourier transform. I have I had the covariance field, the covariance of my drift field divided by p squared, 1 minus cos p squared. So I have k trace, I goes from 1 to 2, k I p, this was my covariance, divided by p squared, dp. But remember what was k sub I, that was p tilde, remember what it was there on that blackboard. So if you put together things, when you take the trace of k, the trace of k is just v hat p. So we had v hat p over p squared, dp, where v hat is the Fourier transform of u squared. U was e to the minus x squared, just to be concrete. If u is e to the minus x squared, then v hat p is e to the minus some constant times p squared. It's like this. So I have to integrate 1 over p squared in Rd at the origin. At the infinity, I don't have problem because due to infinite differentiability of everything, this decays exponentially for large p. So at infinity, I don't have problem. I have problem at 0, but this is just not integrable in 2 dimensions. There is no h minus 1. Of course, it's not integrable, and marginally so, because the Gaussian free field is marginally bad or good. Depends on your point of view. I like it, but it's marginally not the usual stuff. Good, so h minus 1 fails. Let's go to the variational formula. And if you page back in your notes to the first week or the first lecture, I gave you a variational formula which was the following, that r phi r lambda is the resolvent of the semigroup. And I gave you the infinitesimal generator that was there, so it's a concrete object. And the variational formula was the following, that is equal to supremum over all psi's in the Hilbert space. Phi is now that fixed phi. All psi's in the Hilbert space of twice psi phi minus psi identity, lambda identity plus s psi minus a psi lambda identity plus s inverse a psi. Mind that this s is minus Laplacian in our case. To be more concrete, I write it like that. right? And as I told you, this gives immediately the h minus 1 upper bound and the way to find the lower bound. So this gives me an upper bound and a lower bound. So I write r lambda phi is less than or equal to, I got the upper bound just forgetting about this. If I forget about this, take supremum over that, elementary linear algebra, if you wish, gives me that this supremum taken over, that taken over the first two terms, will give you just phi lambda identity minus Laplacian inverse phi. But these are very concrete objects. You can compute them. This is computable. You compute it, you see, when you look at the paper how it's computed, it's explicit computation. Knowing the Gaussian free field covariances and knowing ordinary Brownian motion, how it behaves, you can compute this. You get for this one something like c times log lambda. And that's how we get the upper bound. That's cheap. And we get the lower bound, which is the interesting one, by taking supremum. It's difficult to take supremum over all Hilbert space. Try to take in a subspace, cleverly chosen subspace. Since my phi is in H1, is in the first subspace, maybe it helps to take in the first subspace. So let's take in the first subspace. So it's greater than supremum when psi is in H1 of the same thing. What does it mean that psi is in H1? It's a Gaussian. It's a linear combination of my fields. So try to find this, right? By the way, I didn't say in advance, but let me give some historical remarks which I forgot to make. As so much in all this theory, the origins of this variational principle and all that are also in the work of Varadhan and co-authors. So origin of variational formula and applications of variational formula, Varadhan, co-authors. There are papers where these are late 90s, early 2000s, right? There are other names to be mentioned here. Komorowski and Olla. And I don't have time to list all, and probably I would forget, but there is a very crucial and important paper by Quostel, Zalmhofer, Landim, and Yao. And the method, the basic approach is taken from there. There are variations, so it's not the case that you just copy what's done there, but ideas are taken from there. So that's for the historical correctness. So now I have a variational problem formulated here. Here is my variational problem, and let me see how can I make these things. So I will concentrate on the lower bound, because that's the interesting one. That gives the super diffusive behavior. Give me a second. So I do the following. I choose psi of omega is a linear combination of the omegas. It's from the first subspace. The first subspace contains linear combinations of my Gaussians which define the problem. So it's chosen like integral on R2 of u of x, u is a vector field, dot omega x dx. U is a test function. U is a test function. I want to optimize. I want to find a good test function. Mind that this must be in L2 that imposes something on square integrability of U. There is some condition on U because otherwise you must stay in L2. But if you choose a proper test function, then you are right. Right? Since this is divergence free, better you choose U. I reduce the by symmetries because I don't want to work for nothing. I don't get more if I take here components which are orthogonal to that. I don't get more. So better choose U divergence free. So let div U be 0. So that's a condition which is it's not imposed, but anyway, the extreme will be achieved by someone like that. Don't gain more from others. Yes? And actually, better change for computational reasons. This is a divergence-free field, the divergence-free vector field. This is not random anymore. On R2, better take the height function to which this guy is the curl. So better say that Vx, that V is, okay, V is rot I times, for some reason, which doesn't matter much, rot of U. That means that this has two components. V will be a scalar field, means that V of x is d by dy U1 minus d by dx U2 multiplied with an I. And you get the height function to which U is the curl or something like that. Or to which U is something with the anyway, it just changed the function because this is more handy. This will be more handy for us. I will write down the variational problem. We will arrive to a variational problem to solve. Down to earth in R2, right? And I make it as simple as I can. So this, okay, this makes V hat P will be P times U hat P, and vectorial product means what you know that vectorial product is. Question?
Define the roots.
Say it again.
Define the V.
V is the rotation of U.
How do you rotate?
Rotation, that means that V of xy, say, okay, V of x is d by dx2 of u1 of x at x minus d by dx1 of u2 of x. Okay? So in 2 dimensions, curl and rotation are dual, are adjoint things of each other. Right? And take apart. So this means that I will work anyway, I will work in Fourier transform. So this is how to. Anyway, I write down the terms. Let me call, do I have? Yes, let me call this one the first term. Let me call this one the second term. And let me call this one the third term. And I write down these 3 terms now with that choices. And no, I wouldn't even call it analysis, it's calculus. It's multivariate calculus what I'm doing. And I get the following. I want to arrive to the variational problem to be solved because it's indeed instructive in a sense. So the first term, with this choice, the first term will be phi psi will be integral on R2 of V hat P by V hat P is e to the minus P squared or something like that, of that sort. So P2 divided by P squared. Yes, by the way, yeah, why P2? Why P2? Because this phi, the function phi is a vector valued function. And I do it for one component of it. Right? I do it for one component. Anyway, so P is the Fourier variable. P2, we are in 2 dimensions. Yes? V hat of P dp. And call this one J1 of V. Or maybe J1 of V hat. V hat is Fourier transform. The first expression. I have a second expression of V, which is this one. I get psi I lambda I minus Laplacian acting on psi. These are very explicit computations. We have to use Gaussian covariances. And I will show you where the Gaussian helps. So far, Gaussian has no much importance, but it will help later. Is equal to integral on R2 of V hat of P of lambda plus P squared, comes from here, divided by P squared, and Vp squared dp, and call this guy J2 of V hat. And the third one, now the third one is tricky. The first two are linear essentially. Okay, when I say linear, I mean quadratic. The first is linear, you just have two, these are linear expression in omega, so these are 2-point functions. These are covariances of Gaussians, you have to. But A, mind that A had a multiplication, had these raising and annihilating operators. These are essentially multiplication operators in it. So these will be quadratic in the Gaussian field, and this will be another quadratic expression. So altogether, this is a quartic expression in the Gaussian field. Yeah, so that's that's where Gaussian will help us. Let me not do the computational part, just write down that the third, all computations are to be found in that paper actually, and it's very beautiful computations. So the first, that means A psi Laplace, 1 minus Laplacian inverse A psi, with psi expressed like that, will be, and note, what is that? So if you step back 2 steps, you see this will be a quadratic expression in my Gaussian fields. This will be a green function. In Fourier transform, it will give me a green function. And this will be another quadratic expression. So, and scalar product means integration over the Gaussian measure, right? So this altogether, this means expectation, it's a 4-point function of the Gaussian field. 4-point function of the Gaussian field, which I'm going to write down. So this will give, yes, which I'm going to write down, the result I'm going to write down. And here there is a very important thing I want to remark. So this is a 4-point function. And mind, and this is very important what I'm saying now. 4-point functions of Gaussian fields are expressed in terms of 2-point functions, right? Gaussian, all higher order correlations are expressed in terms of, and these are these classical things of Gaussian. And that helps a lot because it reduces, I don't have to introduce new variables, closes the equation. It will give me a nonlinear variational problem, you will see, but it closes. I don't need other new objects to be introduced. And that's where Gaussian helps. So altogether, after computations, you get a double integral on r squared cross r squared. You have a v hat p, v hat q. This is actually very instructive calculation. So if you want to understand Gaussian fields and all that, do these computations yourself because it's instructive. You have a p scale vectorial product q squared by p squared q squared. You have 1 over lambda plus p minus q squared, and you have vp minus vq squared. May say this is actually the v's are real, so I could say, but squared dp dq. And this is an identity. This is a computation. I don't go give details of identities because those are just computations. Question? Time is done. Gone. Okay, I'm finishing in 1 minute. So I have a variational, as you see, I have a variational problem for the function v, a quadratic variational problem, linear and quadratic terms appear, quadratic variational problem for v sub q. It's a classical problem of analysis. It's not a trivial problem of analysis, but it's a classical problem of analysis. And one last word here, this helps. The vectorial product helps because when P and Q are equal, then bad things happen. Bad things happen when P and Q are equal. Right? Because I have a zero, I have an annihilation down there. This comes, by the way, from this inversion. I have 1 over, at small values of lambda, I have a singularity when P is equal to Q. But the scalar, the vectorial product when P is equal to Q, vectorial product vanishes. So this will help me a lot. And last word, this is a non-trivial variational problem to solve supremum of first minus second minus third. First minus second minus third, explicit thing about a function, can be solved. Not in the sense that I find the optimizer, but I can find a good test function which gives me the log-log lower bound. Good? Thank you.